Okay, so and make the lab, and then you submit the lab report, of course, make sure it looks good and all that stuff. And like I told you before, it's yours, it's your work, it's you're gonna keep it, you're gonna take it with you to the interviews and all that stuff. So give it the time it takes. And then as you're working, if you have any questions, you can bring it up in the class or in the lab or email me, anything like that. All right? Any questions? As far as the project, we spend also a lot of time on the project and the loads and all that stuff. So next step for the project is how to design the slab and how to design the beams, meaning that how much rebars do we need in the slab, and then also because we already calculated the thickness, so we need the rebars now, and then also how much rebars we need for the beams because we already calculated the thickness. So that we're gonna cover in chapter 4, and then we will go to the lab and do that stuff. All right, any questions, guys? All right, this is week. Which week is this? 5 or 6? Anybody?
I think it's 6.
6. Okay. So 2 more weeks for the midterm then. That's good. We have good coverage. All right. So design of rectangular beams and one-way slabs. So let's spend some time on the title. Rectangular beams. We know it's rectangular because we said that has the best moment of inertia. I equal BH cube over 12. You're cubing the depth. So the higher the depth, the bigger I, and the bigger I, the lower the deflection. Remember the formula 5WL to the power 4 over 384 EI. I is in the denominator, so the higher the I, the smaller the deflection. That's why we use rectangular. Okay, design. So far, what we did so far is an analysis, and I mentioned those at the beginning. So far, we did analysis of beams, not design, because the beam was given to us width 12 inches, depth 18 inches, 3 number 6 bars, 3 number 9 bars, and ask us how much moment can this beam carry. This is an analysis. And when you do that, like the homework problems, everybody is going to get the same answer. So we call that a closed-ended solution. Okay, that's an analysis problem, and it's easier than design. That's why we start with analysis. Design, on the other hand, is when you don't have the cross-section. You're the designer, you're the creator. You're gonna create a beam, a rectangular beam with certain dimensions. To do what? To support the loads that are applied. So in this case here, you're gonna be given the loads, and you're gonna design a beam to carry those loads. Okay, same thing for one-way slabs. And we said the one-way slab is when the load can be assumed to go into one direction. Okay, we talked about that a lot. We covered it in 359. So, and then we said that a two-way slab, and usually one-way slab usually is a rectangular look. You know, close to a square look slab, that's a two-way slab, and that's not covered in this class because it's an advanced topic. Usually if you take advanced concrete, you will cover that for sure. All right, so that's the title. See how we can talk a lot about the title, and it's so important. From beginning I told you that I'd like you to know what you're studying, why you're studying, where you've been, where you're going. Makes a lot of sense for you to understand. Otherwise, you're just doing things and memorizing stuff. Oh, this is design, or this is analysis, what is it? And so no, that's why I spend time on the titles, so you know where you go. Okay. So load factors. This topic was covered at the end of chapter 1. So all we need from here is, and I think we did that in chapter 1, this is where we said 1.2 dead load, 1.6 live load, and we added the earthquake load and the wind load and all that. But for this class, most of the time is, if you have a dead load and a live load, it's 1.2 dead load plus 1.6 live load. And we're going to do it a million times. That's the combination you need. If you only have a dead load, like we saw in the columns, remember when we said the own weight of the column, that was only dead load. So we don't say 1.2 dead load. No, we say 1.4 dead load, because that's the only load we have. And that's what the code said. Even if you have a live load, if the dead load is larger than the live load, and you say 1.4, you have to check 1.4 dead load, and you have to check 1.2 dead load plus 1.6 live load. Whichever bigger is your PU. All right, so we'll talk about that. So design of rectangular beams. So how do we design beams? Look at that. There's 3 different ways of designing that, and you will see. You will see how we do that. Okay, the first one, it says beams 20 to 25 foot long. These are the actual sizes, the civil engineering sizes, the practical sizes out there. We don't design beams that are 5 feet long or 4 feet long. Our beams are 20 feet long, 25 feet long. Why? Because if you're in a commercial building, the distance between the columns usually is about 25, 20. Look at our project. One dimension was 30, the other one was 40, right? So that's where. So it says that beams 20 to 25 foot long, D over B approximately 1.5 to 2. So what's a D? D is the distance from center line of the steel to the top, and B is the width of the beam. So D over B approximately 1.5 to 2. And remember, in our approximation for the DT beam, I said use 2. Right? Use 2. So between those 2 is fine. Longer beams, let's say the 40-foot beam, you might want to approximately D over B 3 to 4. But even it doesn't matter which number you used, this is an assumption, you're gonna be able to tell whether this was the good or not as you go. But you have to start somewhere. Shallower beams result in reduced floor height. Okay, that means if I make my beam 20 inches high instead of 40 inches, over 100-story building is going to make a big difference. So we try to make our beam shallower, right? So shallower, reduced in floor height, and if you reduce the floor height, you reduce the building height. And if you reduce the building height, what happens? You reduce the wind load, because the wind load is pushing on that building. Overall, beam dimensions are usually in whole inches. You don't make a beam that 11.75 inch by 21.625 inch. No, whole numbers. You round up. Okay. Beam width are usually in multiples of 2 or 3, like 12, 14, 16. We usually like even numbers. You can use odd, but we usually like even numbers. 10, 12, 14, 16, 18, and all that stuff. You can use odd, no problem. See, those are just guidelines for you to, when you start proportioning the beams, you're gonna see, and you will see how we do that in examples. Deflections. Deflections may be calculated. Okay, how do we calculate that? From 359, like I said, for a beam that is uniformly loaded with a W, the formula for delta is W, the W, 5WL to the power 4 over 384 EI. That's a formula. And we learned in 359, not just to memorize the formula, how you can calculate that, how you can derive that equations. But most of the time, you're going to look in the back of the book and find the formula, whether it's a uniform load or a concentrated load and all that stuff. Short-term and long-term deflections. Some of the deflection is going to happen short-term, meaning that when you apply the load, the deflection is going to take place. That's short-term. Long-term is going to happen over time. Over time due to the sustained load. Sustained load meaning a load that is always there, and that structure is going to start deflecting slowly over time. ACI code provides minimum depth deflection calculations. Okay, ACI provides minimum depth, period. Deflection calculation is not required. That's that table I gave you. So if you use the minimum depth that the table tells you, you don't need to worry about deflection. There's the table. Remember I gave you that. So this is ACI minimum thickness. If you use this table to find the thickness, this is a minimum thickness. You can go over that, but if you even use the minimum, you don't need to worry about deflection. All right, that means these numbers have been beefed up to take care of that. This is very, very important. And then we've used it to size the slab thickness and the beam thickness. So you should know that now. Just a footnote, it says this table and this formula is for normal weight concrete and grade 60 reinforcement. And that's what we're gonna have. Even in real life, 99.9% that's what you have. If you have different than 60, grade 60, then see footnotes for lightweight concrete and other grade. Let's say you have lightweight concrete and different than 60, there's a footnotes to that table that it tells you which factor to multiply it by. But you don't have to worry about it here because we're not gonna use that, all right? If deflections are calculated, ACI minimum values are not mandatory. So if you choose, say, you know what, I'm gonna calculate the deflections. I'm gonna calculate the deflection and compare them with the allowable. The code will also give you an allowable. We're gonna see that in chapter 7. So you can calculate the deflection, and then if you are less than the allowable, you're okay. So if you do that, you don't have to follow these. You can be less than these. But if you're designing something new, highly recommend this. I highly recommend that. When wouldn't you use that? If you are doing an analysis to a project where you were hired to do analysis and the building is there and you analyze. I'll give you an example. I was hired by somebody bought a house in San Diego area. The house was on a 30-acre land, and the person who built the house built an 1,800 or 800 square foot house on a 30 acres. So what happened when he lived there, he went ahead, did a room addition, and he made it 2,000 square feet. The problem is he did not get permits for that. So when he sold the house and the land, he told the buyer, this is the case. So you have to go through the city. And then also code enforcement, somehow they found out about it. So anyway, code enforcement came and said, well, there's a problem, you have to do that. So anyway, the guy hired me to do it, and I did the analysis. So as I was doing the analysis, I checked the thicknesses. They did not meet those. See that? I checked the thickness of the beam, the thickness of the slab. They were less than what this table is. So no problem, I went ahead and calculated the deflections as a result and proved that the deflections are less than the allowable. CD accepted that. See that? You will only do that if you are analyzing an existing building. If you are designing a new building, you will definitely use this. All right, but that's why we give you the tool so you can have it both. All right, so here you go. If deflections are calculated, like I did, ACI minimum values are not mandatory. You can violate those. But if deflection are calculated, you have to compare them with the allowable. And the code gives you that. We will see that. ACI minimum apply only to members supporting construction not likely to be damaged by large deflections. Okay? So these minimums that we're talking about are applicable only to members supporting construction not likely. Let's say you have beams and that beam is supporting a concrete slab, but at the bottom of those beams, instead of having a false ceiling made out of foam panels, let's say it's all glass. It's all glass panels at the bottom. What do you think that glass is likely to be damaged by large deflections, right? So if that's the case, then you should not use these values. You should design it and check it against the allowable deflection. And you will see when we check against allowable deflection, it will tell us likely to be damaged by deflection or not likely to be damaged. Because if it is likely to be damaged, the allowable deflection is going to be smaller. If it's not likely to be damaged, then it will be larger. If you have a false ceiling made out of foam, it could probably easily deflect 1 to 2 inches, no damage. But if it's a glass, you probably cannot exceed half an inch, quarter of an inch, right? So that's what this is. But this is very important tip. Okay, member weight. We touched base on that before. Remember when we did the DT beam, we said click that square, so make sure the program calculates the own weight of the beam. So that's what we're talking about. When you have a beam, like we mentioned here, 25 foot long, you can imagine 25 foot long, and then 14 inches wide by 26 inches deep. Can you imagine the weight of that beam? It's very heavy. Every cubic foot of that weighs 150 pounds. So that beam is going to carry the load coming from the floor to it. But guess what? Somebody has to carry the weight of the beam itself. So we add that weight to the applied load. So the beam carries itself and the slab above that. That's what this means. So it says the weight of a member is a load which must be supported by the member. You cannot only just calculate the load coming from the slab to it. You have to calculate the own weight. And we will do that in many examples. Member weight is not known until the member is designed. So if I'm going to design a beam 25 feet long, I don't know its dimensions. So how can I know how much it weighs if I don't know the size of it? That's what this is saying. It says member weight is not known until the member is designed. Estimate the member weight. So we estimate the member weight. What did I say before? We can estimate anything as long as we check it. Estimate the member weight, design the beam, refine the estimate member weight. So we're going to estimate, let's say it weighs 400 pounds per foot. When I estimate the weight, then I can design the beam, then I find its size. When I have the size, I will calculate how much it weighs. I'll compare it to the 400, right? If it's not 400, let's say it came 450, then I will assume the next one that the beam is 450. And repetition, you've done that a lot in your classes and your labs. So trial and error until you are close to what you assume. It could take you 2-3 rounds, that you do. Redesign the member, refine weight, estimate if needed. So again, you keep trial and error. Give me a sec. Okay, so member weight is that the weight of a member is a load which must be supported by the members. Okay, we said those. Now, so look at this. The only thing that was added to this screen here, let me go back here. See, this was the screen. The next one is instead of estimate, they replace it with a swag. Okay, swag the member weight. Let me guess it. Guess the weight of the member, and you will see how we do it with the examples. So, reinforcing bar selection. Bar diameter is bar size in 1/8 of an inch through number 8. Meaning that, remember we said that before. Any bars from number 8 and below, you can find the diameter of it by dividing the bar number by 8. So for example, bar number 4 bar is, what is the diameter of number 4? Is 4 divided by 8, is half inch. What is the diameter of number 8 bar? Is 8 over 8, which is 1 inch. What is the diameter of number 6? 6 over 8, and so forth. But what is the diameter of number 9? Is not 9 over 8. It's going to be a little bit off. How do we get that? You don't have to calculate. It's really pi r square, but you don't have to calculate that. You go to the table and read the numbers. Okay? It says larger bars are slightly different. Very small difference, but they are different. Diameter of a number 6 bar is approximately, see that 6 over 8, so it's 3 over 4. bar areas. So text appendix table A4 or next slide. So what is the area of the bars is you go to back, and please start getting familiar with the tables in the back. Or next slide, which is here. We will talk about that. It says don't mix bar sizes. Tension steel. That, when you select the bars for the beam, don't say, oh, I want to use 2 number 4 and 2 number 6. No, try to keep the same numbers. Can you do it in theory? Yes, it can be done, as long as we meet the total area of steel. But it's not a good practice. It's an area where the contractor could make a mistake. Or 2 number 6 and 2 number 8. He could put 3 number 6 and 1 number 8 by mistake. See that? That's why we don't do that. We don't mix that, unless if you have to. You say you're doing a job and you only have few bars left, and then yes, you can do it as long as you're careful. Don't mix bar sizes, tension steel, compression steel, or stirrups. So keep the same bar sizes. All right. Reinforcing bar properties. So when we say a bar, we saw that in chapter 1 or 2, I believe, 1. So in this country, we have bars from number 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, 18. That's it. Those are the bars. You can get number 2. We call those pencil bars. Remember, we in the lab we saw the pencil bar, but they're not used a lot. They're very, very small. So these are the standards that this country goes by, which means you will not find a bar number 12. You will not find a bar number 13. They don't make it. You're not going to find a 15 or a 16 or a 17. They are not made. Why? Because every manufacturer follows the country's requirements. Okay, ASTM and all that. So this is the bars. If you are in a different country, especially in the metric system, they are completely different. Because remember, we are in inches, they are in millimeters or centimeters. So those bars from those countries are, usually they start with, you have number 6 millimeter is the smallest. 6, 8, 10, 12, 14, 16, 18, 20, and then so forth. So whichever country you are in, you study that, and very simple, it's just different properties. So instead of inch diameter, it'll be millimeters. And instead of inch square area, it'll be in millimeter square. But this is it. So anyway, number 6 bars, the diameter of it is 6/8, which is 0.75 inches. The area is 0.44. Okay, so don't try to calculate the area from here, because if you have the diameter, you can calculate the area of a circle. But no, go to the table and get this number. This is more accurate. Okay? If you don't have it, then yes. Okay, cover and stirrups. See that? If you notice that we are defining some terms before we start designing the beams. This is what we need when we start designing. So what is cover? What is cover? Remember, the cover is how we're going to cover the rebars. And remember, in beams, I told you that distance is 2.5 to 3 inches from center line to the bottom of the beam. You will see in the slabs is much less than that. It's like 1.75. But we'll see those. So that's what the cover is. Stirrups. What's the stirrups? Stirrups is the shear reinforcement in the beam that we're going to cover in chapter 8. And you will see that. Say stirrups are used for shear reinforcement. Okay, again, we said the beam is going to be subjected to this force, that's shear, in addition to bending. So that's what we use. And to position top bars. Okay, so we use it for shear, and also if we're going to put top bars in the beam, something has to hold those. So those stirrups will do that. Let me see if we have pictures right there. So let me skip to that. So there's the beam.
I left it there on purpose.
So let's define the cover. I've been saying at the beginning from center line to the bottom. The cover is actually really from the edge. So let me explain this. So there's your bars. 3 number 10 bars. There's the stirrups that's gonna resist the shear. The diameter of the stirrup is most of the time 3/8, it's number 3. This DS is 3/8. So the actual cover we're talking about is really from the edge of that to the bottom. It's 1.5 inch cover, minimum. Now, the 2 inches and 2.5 and 3 inches were from the center line to the bottom. See that? So from here to there will make the difference. But when I said 2.5, if you do 2.5 or 3 inches, you're gonna be able to meet this no problem. All right, so that's what that is. And look at this, number 3 stirrups. And so one reason we use that is for the shear reinforcement. Second, what if you have 2 top bars, and we will see that. Sometimes you have to put bars at the top. How are you gonna hold those? These gonna hold them. We call them hangers. So you're gonna put this and then tie this bar with that with a fine wire. Okay. And then here all the diameters and all that stuff. We're not gonna go into a lot of details like that, but please, for the first time, just study that, and you will see when we start designing, you'll be able to do. It says here minimum edge distance. What is the minimum edge distance? Like again, this one here. Again, we're not gonna do all that stuff. You will see. We'll give you a method you can do that, but it's there. So there we go. Stirrups are used for shear reinforcement and to position top bars. Minimum stirrup size for number 10 and smaller. So number 10 bars and smaller. If these are number 10 and smaller, the minimum size of these is number 3. Right there. The smaller is longitudinal bars is 3/8. That means number 3. Okay. If the bars go more than number 10, so let's look at that. So up to here you can use number 3. 11, 14, 18 you have to use number 4 as a minimum. Who said that? The code. Okay. Minimum stirrup size for number 11 and larger is 1.5 inch in number 4 bars. See that? Number 11 and larger right there from here to there. We only have 3 bars. Minimum inside radius of a 90-degree bend is twice the stirrup diameter. We don't focus on that. He's saying what is the minimum radius of this bend. They just bend it. They just bend it 90 degrees. We don't care about radius. Yeah, I just want you to focus on what you need. Otherwise, yeah, you can memorize this, you'll never use it. So what do you do with that? And then most of the time, these things, the draftsman will take care of it. You as an engineer, you don't touch that. The draftsman will do. Okay. Reinforcing bar cover. Cover is the distance from surface of a bar to closest concrete surface. Right here. Where's the surface of the bar? Right there. Not the surface of this bar because there's a bar underneath. The idea when I say cover, I'm gonna cover all the steel inside the beam so that moisture doesn't get there, it doesn't rust. Salt wind and all that doesn't, salty wind and salty environment doesn't attack, so you have to cover it. So that's what we're saying, right here. This is the cover, okay? Cover is the distance from surface of a bar to closest concrete surface. So if I look at this bar, what is the closest concrete surface? This. So this is a cover. What happens if I look at this? It's from this to there. That's also a concrete cover. From here to there, concrete cover. Here, from here to there is concrete. Okay, so that's what it says. Again, cover is the distance from the surface of a bar to closest concrete surface. That bar doesn't have to be the main bar. It can be the stirrups, because like I said, the idea is to protect it from environment. Section so-so of ACI specifies cover values. The code will tell you what is the cover values. Okay, we'll see that. Okay. Different cover requirements for cast in place, precast, and pre-stress concrete. It depends what kind of concrete we're using, the code will give you a different cover requirement. We'll see that. Special exposure requirements also, again, the code will tell you that if you're building a building along the ocean where, you know, salt water environment and all that, that the code will take care of that. Okay, so we talked about this. It says minimum edge distance. Again, we will discuss this in the example and you will see how we do that. So don't get lost here. Don't be intimidated by all this, but it'll all work out. Okay, a few more slides, then we can start designing now. Minimum spacing of bars. So if you're doing this, what is this minimum space between a bar and a bar? See that? So we're doing that so when we start designing, we know. ACI say minimum clear distance between bars is the larger of the bar diameter or 1 inch. When I say clear distance, is the not center to center. So that means it's from here. Sorry about that, should be vertical line to there. Okay? From here to there. See that? That's the clear distance. It says it's the minimum distance should be the bar diameter or 1 inch, whichever is larger. Okay? Whichever is larger. So if this is number 7 bar, 7 over 8 is the diameter, less than 1 inch. But then you will use 1 inch here. The idea is when you pour concrete, we don't want the aggregates to get stuck between 2 bars and prevent the concrete from coming down. We don't do it too close. Okay, so that's the main idea. So it's the clear distance. So again, this is important. Minimum clear distance between bars is the larger of the bar diameter or 1 inch, whichever is larger. See, it tells you here, the larger of. If layers of bars are used, bars are in the upper layer are required to be placed directly over the lower layer. We can. It's definitely acceptable. You don't do it too much time, but you do. If you're gonna need 2 layers, then you put the second layer, line it up with the first one. That's no problem. See that? If you do that, then your D becomes this distance. From here so that's the idea is the D is from the center of gravity. Center line between. So how much is this spacing you think between the two? It's gonna either be the diameter of the bar or 1 inch. Let's say it's 1 inch, right? So this is gonna be ½ inch above. You can have 3 layers, by the way. I would not go more than 3 layers. If you do 3 layers, so let's say you do 3 layers, then where's your D? The centroid of those 3 layers is gonna be this guy. And then you go from here up. Okay? In my practice, I never had to do that. The most I did was 2 layers, but I never had to do 3 layers. Okay? Because if you have to do that, then you change this section. You don't worry about that.
Professor?
All right. Yes.
What would be some of the reasons why you would put a 1 layer or 2 layers?
Because sometimes your load is high, and then your size of beam is limited for some reason. You cannot go higher than that, and then that means your area of steel is high. So if let's say you need 6 bars, if you try to put all 6 bars in 1 layer, you're gonna violate the minimum distance between bars, right? So you're not gonna have the 1 inch or the bar diameter. If that's the case, then you go ahead and put a second layer on top. Does that make sense?
Yes.
So I'll repeat that. If you cannot, say you have 6 bars, you cannot put all 6 bars in the one layer without violating the minimum spacing, which is the diameter of the bar or 1 inch. If that, then you go 2 layers. That'll give you a space to separate. All right. Any other questions? All right. Very good. Again, those are all practical stuff that you will see. All right. So that's that. So here it says, if layers of bars are used, bars in the upper layer are required to be placed directly over those in the lower. Why is that? Because we don't want, again, the aggregate to get stuck between, with the bars. We want to provide a clear area for the concrete to go all the way down. All right. The code limits maximum aggregate size based on bar spacing. For 3/4 inch maximum aggregate size, maximum bar spacing is 1. And this is the typical in real life. Most of the time, 3/4 is the size we use. Okay, most of concrete mixes out there is 3/4. There's less than that. There's a 1/2 inch. There's an 1/8 of an inch. And let me make a small comment on that. There is a 1/8 of an inch, but remember I said before, 75% of the volume of the concrete is aggregate. So if the volume is that big, the stronger the aggregate, the stronger the mix is going to be. Sometimes, though, people use 1/8 of an inch. We call it in practice pea gravel, because it's so small. The only reason you cannot use that in structures, like in buildings and in parking garages and high rise and all that, cannot do that. The only reason they can do, you can use this for your patio slab, for your sidewalks, for your backyard. If you want to do walkways, you can do that. And the reason people do that, because what happened when they order a load of concrete, they order a pump with it, and they have to pump it from the street to the backyard. And you need a pump for that. So the 3/8 of an inch can be done by a small pump that can be dragged behind a pickup truck. But if you try to pump 3/4 of an inch, no, you can't do that. You need those huge pumps that pumps up into the high rises, like 3, 4, 5, 6 stories. But nobody's gonna rent that for a backyard project. Okay, so, but the structurally speaking is 3/4 inch. That's the size we use. Okay, aggregate size and bar spacing again. Aggregate size limited to 1/5 narrowest dimension, 1/3 slab. This, don't worry about those. This is code stuff, and we don't really. You can read them, but we don't worry about them too much. Again, the way we're gonna design things is gonna work by itself, no problem. Okay, development length. Okay, let me skip and I'll come back to that. No picture of development length. Here you go. I'll go back to that. So what's the development length? Look at this picture here. Let's say this is a balcony. Okay, the balcony usually sticks out of a building, and there's no columns or walls underneath. And we know this is going to deflect down, right? So let me write you the deflection of this under load, exaggerated, is going to look like this. See that? So where's the tension side? The tension is on the top, and the compression is at the bottom. Okay, so when you do that, what do you think would happen if I put my bar here, my steel, and stop it at the end? If I stop my steel at the end here, and let me draw it in yellow. If this is my bar, let me draw it with the deflected shape. It's gonna be here, and I'm gonna stop it here. You think this yellow bar is gonna do anything for me? No, because the maximum moment is here. And then the minute the forms are removed and these loads are pushing down, it's gonna crack right there, and this is gonna go down immediately. I guarantee you that. So what's gonna hold that is the steel, of course, on top, but we have to extend the steel into the support, like this could be a longer beam. This could be a beam going all the way down like this, okay, and then sticking out for a balcony. So here you will have a support, and then here you will have a support, and so forth. Or this could be a column. So when you extend your bar into the column, the beam, what happened when this is trying to deflect down, as if it's trying to pull the bar out. It's trying to pull the bar. And then what's going to hold that bar? That, remember those ribs? It's going to create friction and then hold it. That's what hold that. So you cannot stop the bar here. The distance from here to there is called development. You know that? The distance from here to how much you extend it is called development length. We call it L sub D. Okay? So as a rule of thumb, there's of course equations for that, and we're going to learn that in chapter 7. How much do I extend my bar in? There's the equations, and you will find that. We'll study it. For rule of thumb, if you don't want to worry about equations and you can be on the safe side, it's always, if you use 50, this is practice, times the diameter of the bar, you will always be right. So you take the diameter of the bar. Let's say the diameter of this bar is number 8. Diameter is 1 inch. You multiply by 50 is 50 inch. So you extend the bar 50 inches into there. That's, and you will see when we do the examples, most of the time this number is going to be very close. So please write it down. As a rule of thumb, your LD needs to be approximately 50 times the diameter of the bar that you're trying to extend. Any questions? So that's the development length before we start discussing that. All right, let's go back to where we start talking about it. See, a lot of sheets, but he should have shown that there. Development length. Okay, development length varies with cover and bar spacing. Okay, also how much cover, what is the bar spacing? We will definitely see when we apply the formulas, all that's going to come into there. Larger values of cover and or bar spacing result in smaller development length. Okay, we will see about that. It may be economical to increase cover and or bar spacing in order to reduce development length. But the development length is not a big deal, really. So what, your bar is 2 feet longer or 3 feet longer? Not a big deal. Unless if you are in a critical situation, then you start looking into, okay, what does the load allow me to do? But otherwise, it's not a critical thing. Now, minimum beam width, beam minimum. See all this here? You don't need to worry about that. Because you will see when we start doing that, there's a table in the back. You just go to the back and look it up, and it will tell you what is the beam minimum. Those values came from here, but I don't want you to do that. It's too much stuff that you don't need to do that. Okay? You can read it, see how it's come out, but use the table. That's it. And we will do it a lot. There you go. Table A5 gives you minimum beam width. Why is the beam width here important? So you can fit the number of bars you selected. Let's say you selected 6 number 8 bars. Then you go to this table and find for 6 number 8 bars, what is the minimum width of beam I need so that I can meet the code requirement for the clear spacing between bars. It will give you that value. All right? Design aids, you will see that if you go to table 8 through 13, those tables are RN versus rho. We're going to do a lot of that. Okay? So once you know RN, you can pick rho, and then these equations came from here. We went through that, I believe, so I'm not going to repeat that. AS equal rho BD. This is the equation. Then you sub MU is equal to that. MU over phi BD squared. That's very important. So we're going to have the moment. Phi is most of the time 0.9. B is the width of the beam. D is the depth. then we calculate that, we call it R sub n, and then we enter and get the rho. And you will see, we'll illustrate it. Lateral supports for beams. Lateral support for beam, if your beam is like this, like my hand, lateral support meaning that what is going to be supporting this beam so it doesn't tip or buckle in the horizontal plane, right? That's the lateral support. Concrete beams of normal proportions do not buckle laterally. They don't buckle, okay? Unless significant torsion is applied. Usually that's not a problem. Where this is a problem in steel beams, especially in bridges. If you're driving and you're stuck in traffic under a steel bridge, look up and see. You will see the steel girders. There's a girder here, there's a girder here, usually it's about 6 to 8 feet apart. They have a smaller beam in between. That smaller beam is not carrying any slab load or any traffic. Its function is only not to allow the beam to move in the lateral plane, the horizontal plane, or buckle. So that's what that is. But concrete is too thick and too stiff to do that. ACI code states that lateral support is not required at intervals less than 50 times B. Least width, again, don't worry about that. So in the concrete, it's not gonna trigger that. If significant torsion is present, situation must be evaluated to determine placement of. Yes, if you have a torsion, yes, then you have to do. And what did we say torsion was? Torsion is when you have a slab. When you have a slab like this book I'm holding, and you have a beam on this side and a beam on that side. This beam is loaded only from one side, so therefore it's going to have a torsion to it. Remember in deformable bodies, showed you a beam with a T along the beam. That's a torsion. It comes from the fact that this beam is holding a slab on one side only. But if the beam is holding slab on both sides, they're going to equate themselves. So there's not going to be a problem. All right. So in that case, then you have to think about lateral supports. But usually, even in that case, in concrete design, the slab itself is going to be stiff enough. It's not going to allow the beam to move in the horizontal. So it's never been a problem in my career. That's why it says if significant torsion, okay, and usual torsion is not a problem. Sometimes we call deep beams. That's a beam very deep, okay? Anything over 36 inch in dimension is considered deep beam. That means the depth of the beam is 36. Usually in buildings, we don't have that problem. Our beams are going to be 24, 26 inches, 28 inches. Where would you have something like this? In parking garages. Because remember, the parking garages, you're going to have the beams, the columns spaced at about let's say 9 feet on centers. Because the parking stall is 9 feet, so they usually put one at each end of a parking stall. Let me get off on tangent just a little bit here. Somebody could say, why so close?
What happened?
The reason we put him so close, and then look, when you go into parking garages, you look and see. The reason we put him so close because the span is very long. The span, think about this, a parking garage, you come in, you have a car parked on the left, a car parked on the right, and there's a driving aisle between them. While the parking space on the left is 20 feet long, roughly. The other parking on the right side is 20 feet, so that's 40. You need a 25 foot for a two-way traffic, that's 65. 65. You don't want any columns in there, right? You want to park and drive with no columns. So your span is 65 feet. We cut it down to 63. We make the 20s, we make them 19, sometimes 18, depends on the city standards. But if you're comfortable, make them 20. It's the best. 19, yes, we use 19 sometimes. So if that's your span length, the moment is WL square over 8. L square, see that? You're squaring the length. So the longer the beam, the higher the moment is going to be. So what can you do to manage that? You can reduce the W, the load. How do you reduce the load? By reducing the tributary area. So if my beams are if my columns are 9 foot apart, that means the beams are 9 foot apart. That means the tributary width is 9 foot, 4.5 from this side, 4.5 from that side. That will give you a reasonable number dimensions for your columns and your beams. I'm just got off on a little tangent here. Okay, so that's usually the case. Now, so 9 feet on center. What happened on the ground floor? You need an entrance to the parking garage. You cannot say I'm gonna enter between those 9 foot columns, 9 foot space column. No, you're gonna at least delete 1 or 2 columns, right? So if you delete 1, then your span is 18 feet. If you delete 2, then your span is 27 feet. Okay, that's along the span. And what happened? And that's on the first floor. What happened on the second floor? Your beams are still on 9 feet on centers. So those columns, so those columns gonna sit on that beam. So therefore that beam is gonna be very hefty. Okay? Look when you drive into a parking garage, you'll see it. But you're not gonna see a beam there because the architects hide that. They make it look like it's a piece of precast concrete hanging on the side, but it's really a beam. It's reinforced beam that you don't see that. Okay, so in those cases, your beams will be 36 inches deep. Okay, that's a deep beam. But in buildings, you're not gonna hit that. So if that's the case, what the code tells us, this is your main steel, remember, for bending. But in addition to that, we have to put these reinforcement. We call them skin reinforcement on each side. We're not gonna worry about that in this class, but I just want you to know what skin reinforcement is for, and then where do we use this? All right. So that's that. Skin reinforcement for beams. Again, beams with web depth exceeding 3 feet. See that? 36 inches. Tend to develop excessive wide cracks in the upper part of the tension zone. So if you don't do that, you're gonna start seeing cracks here. That's why you put more rebars. Adding additional longitudinal reinforcement in the tension zone reduces these cracks. Look where we're putting the steel, because the neutral axis is somewhere here. So we put those steel in the tension zone. We don't need them up here because the concrete is compressing itself. ACI code states that skin reinforcement must be provided for beams deeper than 36 inches. See, I said that. The code say any beam deeper than 36, you have to provide that. But again, we're not going to see that in our class. I just want you to hear about it. Skin reinforcement must be uniformly distributed along both faces. See that? We put them on this face and that face, and look how uniformly distributed they are. Right? See, look at this. This is the same distance as that, the same distance as that, they're all the same. Skin reinforcement must be provided for a distance of h/2 from the tension zone face. So, meaning that the tension face is here, so h is the depth and half of it. So from half of the beam down, you provide that. And then this way you don't have to worry about where the neutral axis is. Close enough. Skin reinforcement must be uniformly distributed along both faces. Skin reinforcement, we said that already. Okay. Skin reinforcement may be considered to add to the strength of the beam, but I would not count on that. You know, it's definitely going to add, but I would not count on it. I would only count on the main reinforcement. ACI code does not specify area for skin reinforcement. See, it doesn't tell you what you need. You use your engineering judgment. I would use number 4, small bars, not too big. Number 4, number 5 maximum. Deep beams may require additional shear reinforcement, and this additional steel may be larger than the skin reinforcement. In this case, the former requirement. Don't worry about that. He's saying that the skin reinforcement might require a bigger shear reinforcement, which is understandable. So now beam sizes. Okay, that's where we go back to sizing the beams. Only a few beam sizes should be used in a particular floor system. If you have a floor system you should use only one size. Okay? Although really you could change the size of the beams. Why? Because a beam on the outside is only carrying slab on one side, so the tributary area is small. A beam in the middle is carrying slab from both sides. So in theory, the middle beams needs to be bigger than the side beams. But for practical reasons and economy and ease of installation, you make them all the same. If you have to change, then only a few beam sizes should be used. Try to minimize the number. Sometimes where do we also use smaller beams? Let's say we have, like in the project, I showed you an opening for elevators and staircases. When you have an opening like this, you don't just punch an opening in the slab. You have to put beams around the opening. Those beams can be smaller, but that's what he means by only put few beams, not too much. Beam subjected to largest moment should be sized to be as small as practical. So beam subjected to largest moment. You will take the largest moment on your floor and you size your beam to that and make it as small as possible. Why? Because you're gonna repeat that beam for smaller moments. That's why he's saying that. Size other beams in the floor system similarly and use less steel for those beams that support smaller moments. So yes, I'm using the same size beam all over the slab, the floor, but my edge beam is carrying less load. So guess what? The steel in that beam is gonna be less than the steel in the middle beam. That's how we're gonna accommodate that. Does that make sense? So that's that. Look at this. We still discuss what it takes, but when we start designing, you'll see it's not that bad. But we have to give you all this stuff. This way, when you start designing and you have a question, you go back to these. You go back to the book and see it talks about that. That makes sense. It will answer a lot of the why questions. Bundle bars. Sometimes, let me go back to the beam here. This beam. Sometimes another thing, if I don't want to do 2 layers and 3 layers like we said, I can bundle these bars, meaning I can put 2 bars on top of each other. Or I can put a bar here on top. Or I put a bar on the side. It's okay as long as I don't violate the clear distance. Or you can do 3 bars. That's called bundle bars. That's allowed. Okay? Allowed by code. So let's look at that. So you can bundle bars like side to side, up and down. You can do this, you can do this, you can do. The most efficient one from my experience is this guy. When you stack 2 on top of each other, you don't violate the clear spacing between that. This will affect the clear spacing. This will affect, this will affect, this will affect. Again, in my practice, very seldom I had to do this. And when I had to do it, I went with this arrangement. Okay, so you don't do it a lot, but sometimes you have to. So you do that. So the code allows bundle bars. As many as 4 bars can be bundled. Okay, bundle bars must be enclosed in stirrups or ties. If you do that, then you have to put a stirrup around it. You cannot just put 4 bars like this and then leave them like that. No, the stirrup has to come this way and then go around to hold them. Otherwise, when they start pouring, they're gonna fly all over the place. Bars larger than number 11 may not be bundled. If this is number 11 bar, okay, you cannot too big to bundle that. Usually it's done for number 5, number 6, number 7. Okay. For spacing and cover requirements, consider bundle to be a single bar with equivalent diameter. So you need to consider this with an equivalent diameter of the 2, okay? When individual bars in the bundle are cut off points should be staggered. If you have bundled bars like this, and there's a cutoff point between the two, I mean, as you go along, let's say this is the bars in my fingers here, and then if you're gonna cut them, don't do that. What you do is cut one at point, continue the other one, and then cut the other one later. That means you are staggering the cut, because if you cut them at the same location, you have a weak point. So it says stagger that. Okay, bundle bars must be enclosed. Bundle bars may not be bundled and all that. So stagger, you know what stagger means. Okay, they don't align. According to ACI code, stagger must be at least 40 bar diameters. Okay, stagger must be at least 40 bar diameters. See that? Remember I mentioned 50 bar diameter earlier? This is close to that. See that? 40, 50. But stick to the 50. 50 is safe and easy to remember. You do that. Even here, if you want to use 50, fine. Okay? It says at least. Cantilever beams. That's what we already mentioned at the balcony. Cantilever beams are subject to negative moment throughout the length. Okay? It's right there. Right? Why is that? Let me just get off on a little tangent here. What happened here? Okay. I can see my screen. Can you see my screen again?
Yeah, we can see it now.
Okay. It was dropped off, right?
Yeah, but
Okay, I don't know why, but it did. Okay. So if I do that, let me just show you the moment diagram for this. Let's say it's uniformly loaded. See how important moment diagrams, guys, are? The moment diagram for a uniformly loaded beam looks like this. So this is a negative moment. Maximum at the support 0 here. So that's what he's saying. This beam is seeing negative moment throughout its length. That's how the moment diagram looks like. Okay? So cantilever beam are subject to negative moment throughout the length. You saw that. For cantilever beam, the largest moment occurs at the face of the support. Exactly at the face of the support where and I showed you that the diagram. For cantilever beam, the largest steel requirement occurs at the face of the support. Okay? So again, the largest steel you need is here. Why? Because that's the moment. What happens when you get to this area? You don't need a lot of steel because look at your moment, very small. But what we do in real life, we don't do that. We just carry the steel all the way. If it's a major job, in theory, you can cut your bars here and use a smaller bar to continue, and you overlap that. And that overlap, again, how much do I overlap? 50 dB, 50 times the diameter. And if you have two different size diameters, use the larger diameter, 50 times the larger diameter. Okay? So that's what this is saying. So let me erase the moment here. Any question? So this is a cantilever beam. Next one is continuous beam. What's a continuous beam? This is a continuous beam. It's not a good sketch, but I think you get the idea. Those are beams, and then this is the beam or support. This could be columns, and a beam running on top. That's a continuous beam because how many slabs I have? 1, 2, 3 slabs. I would have drawn these smaller so you can see it, but that's okay. So that's a continuous beam. Well, guess what? When we design the slab, it looks exactly the same. This could be the slab sitting over the floor beams. Remember in DT beam we covered that. So continuous beams are statically indeterminate. Absolutely. Because remember 359, structural analysis was for determinate structures. That means I can solve these problems by statics only. Summation of f of x equals 0, summation of f of y equals 0, summation of moment equals 0. That makes the beam determinate. Here it's indeterminate because highly indeterminate. You cannot solve it by those simple equations. So continuous beams are statically indeterminate. Both positive and negative moments occur in the continuous beam. Okay, let me show you that. Again, we learn a lot from deflections. So if this beam is loaded with you, again, I'm assuming uniform load all the time. How is this beam going to deflect? This beam is going to deflect like this. Exaggerated, of course. Okay, exaggerated. This is how it's going to deflect. Makes sense, right? Because there's nothing here, so the beam is going to go down between the supports. There's a support here. In order to stay continuous, it's going to do that. Nothing in between is going to go down. It's going to go continuous. It's going to go over the support. It's going to go down. So that's the deflected shape. All right. Now, let me change colors here. So what did we say from day one? The steel goes on the tension side. So where's the tension side in the first span? At the bottom. Look at the graph. It's getting longer. That's the tension side. So where do we put the steel on the tension side? That's where this dashed line is. See that? Now, how about over the support? Where's the tension side? Right there. See that? This is getting longer. Where do we put the steel? On the top. Okay? How about this? Tension side at the bottom. We put the steel at the bottom. How about here? Look at the top. Top. And then same thing at the bottom. Now, at the ends, I'm showing the deflection shape like this. I'm assuming a pin support. But in concrete, is usually it's a fixed support because we put it monolithic. So what happened? If it is monolithic and you have a fixed support, you're going to have a negative here, negative moment. So therefore we put a steel right there. Okay, and then we put steel. In the project, I told you to assume it's a pin support, so you don't do that. Okay, but in theory, we need some steel there. Any question on that? Now, somebody could say, okay, fine. What happened here in between? Do I leave this like that? No. Usually we go ahead and add a small bar just to attach the two. But that's your main steel I showed you. The other one is minimum steel. Okay, that's one thing. So you add him there to do that. Second question is, how much do I extend this bar into the support? How much? The code say you extend this 6 inches into the support. I don't like that. I like to take my steel and extend it all the way to the end here. Minimum to the center line. Then I take the other steel and I extend it to the end of that. See that? So over the support I have these. If push comes to shove, at least the center line of the beam, but not 6 inches. Okay? Although 6 inches is fine, but practically speaking, it's better to have your bar anchored into the support better. All right? So that's that. And notice that the book doesn't talk about that. This is just practice. Okay? It doesn't talk about that. So any question on that? All right. So let's see what the, before we erase that. So it says both positive and negative moment occur at the continuous beam. What is this moment here? Positive. What is this moment here? Negative. Positive, negative, positive, negative. Okay, that's what happened. The largest negative moment occurs over the support. So, and let me see if there's any more on both positive, negative moment reinforcing is equal. See, both positive and negative moment is required. So that's why we said we put the steel at the negative moment, positive moment. So that's both required. So the largest, I want to talk about this one. The largest negative moment occurs over the supports. See that? And then the largest positive moment occurs near midspan. So remember, this is positive moment, this is negative moment. The largest negative moment will occur on the support. And usually it's the first interior support. So the largest moment is going to be, this is exterior support. First interior support is this guy. So this moment is going to be the largest. From this side, this is the exterior beam. First interior support from this side is this. So that's going to be the biggest moment. Due to symmetry, this moment equal to that moment. Okay, and I will draw a moment diagram first in a second. Any question before I erase these lines? Okay. So let me clean this beam.
Professor?
Yes.
Just real quick, why did we need reinforcing steel again at the end of the supports?
Yes. The end of the support because in here, in real life, when you put a beam and a column and whether it's a column or a beam. Let's say this is beam and this is beam. That's okay. You put them monolithic together, so the concrete forms a fixed connection. Versus if you take a steel column and you attach a steel beam to it with bolts, that's not fixed. So if that's the case, then we will develop a negative moment here, because this is continuous. Okay, it's not a simply supported. It's a fixed in per se. Okay, so that's why it does that, and I will explain it when I draw the shear moment diagram. Any other questions? Okay, so let me clean this, and I will draw the diagram, the moment diagram. All right. So let's draw the moment diagram and show you how this works. So the moment diagram for a simply supported beam is going to be like this. You're going to have a negative moment here. And it's going to go up like this. And it's going to go up like this. And it's going to go up like this. This is the moment diagram. Okay? See, there is a negative moment here. That negative moment requires steel right there. The first interior support, this guy is usually the largest moment. Largest moment. By equation, WL square over 10. Okay, approximately WL square over 10, meaning the W on the beam, L is the span length over 10. It gives you a very good estimate for that. Now, if you look from this end, this is the first interior support. Due to symmetry, this is equal to that. What about this guy here? This guy is WL square over 24, roughly. Very small, see that? How about these? And this says that you have a positive moment here, a positive moment here. This positive moment is larger than that. And this is roughly about WL square over 16, I believe. This is WL square over 18. So this is kind of rough numbers from the ACI code. We're not going to use that. Why? Because guess who's giving us these moments? DT beam. DT beam is going to give us those moments very accurate. Okay? Any question on that?
So do the middle beams, the middle beam gets the most amount of moment in it? Is it because of more load is being pressed onto that area?
Because you have load coming to it from both sides. Where this is here, you have load coming from one side, but not much load coming from the other side. Does that make sense?
Yeah, it makes a lot more sense.
Yes, so that's why. That's why your positive moment in the middle is gonna be larger than the others. Okay? Any other questions? Okay. And I will go back to the comment Allah show, but before that, I want to do one more moment diagram. It's okay. See that? Based on the moment diagram I just drew, look at the moment diagram for this pen. It's right there. Negative moment goes up, negative moment. This one here, negative moment, and that, and then so forth. See that? This is taking these beams individual. All right? I want to draw one more diagram. Let's see. So if another moment diagram, like the way I assumed in the project is pin supported. This is always on the conservative side. If it is pin supported, then the moment diagram looks like this. You don't have a moment at the end. Then you have this right there. See that? See zero moment here, zero moment there. If that's the case, you don't need this rebar. But in real life, you will always have a negative moment due to the fact that this beam and this beam, or this column and that beam, is poured monolithic. If this is a pre-cast concrete where they're not monolithic and they are connected via bolts, then there's no negative moment there. Okay, so that's that. Okay, that's fine. So let me go back just one more detail here. It says, see that the largest negative moment occurs over the supports, and especially the first interior support. The largest positive moment occurs near mid-span. See that? In the middle, not on the sides. Both positive and negative moment reinforcement is required. Okay? So that's what that is. Okay. Now, these are the design examples now. We're going to start now doing what we learned and then apply them, do that. Okay. So let's start
Professor.
Yes.
So that last example, I was just looking at it. You just broke apart that slab and you looked at it as if it was 3 simply supported beams, correct?
In here? Yeah, but they're not simply supported. Remember, look,
right.
Exactly. So you do that. But in real life, we don't really do that. We keep it like this, and then enforce it like this. But this illustrates to you that really, if you take this span, there's a negative moment here and there's a negative moment here. And guess what? This moment is equal to that. And he's just trying to show you the negative and the positive.
Oh, okay.
But we don't, in real life, we do not do this to put this every span separate. No, we design it as continuous. And we will do that. We will do that in the lab, in the project. Any other questions? Okay. So with that, let's do the beam design. So there's the first one, example 4.2. It says design a rectangular beam for a 22 foot long. So the span is 22 feet long. That's L. Simple span. All the examples going to be simply supported because it takes a lot to do continuous, and that's why I like to do the project, because if you don't do the project, you're only going to design simply supported spans. All the books don't give you continuous beams. Very seldom if they do. So 22 feet. Excuse me 1 second. I need to.
Hey, Binyam. Can you hear me?
I can hear.
Sweet. So I'm just looking at this example right now. So the live load, apparently there's a live load and a dead load for this beam. 1 kip foot and then 2 kips per, right?
Yeah, so it's saying sample spanning carrying a dead load of 1 kip per feet, not including beam weight, so you don't include that, and then a live load of 2 kips per feet. So.
Oh, I see. What does it mean again by grade 60 reinforcement?
There's different grades. So you have the 60, the 40, and then the 90. I don't know the other ones. But
oh, yeah.
So for different grades, so you have different requirements for the reinforcements.
That's true. That's true. I mean, I think there's a table for that, I believe. I'll look through it again.
Okay, sorry, my friend. I had to take this call. So I know I heard people asking questions. So do you want to ask me the question, or whoever was asking? Are you okay?
Oh yeah, we were just discussing with some of our fellow classmates, like, because we're analyzing the example. That's all it was. But
okay.
Yeah.
All right. So you're okay?
Yeah. So far, so good. You explained it.
Very good. You're welcome. Sorry, I had to take the call. So it says design a rectangular beam, 22 feet long, simple span, simple supported, carry a dead load of 1 kips per foot, not including beam weight. See, so this is the weight, the load coming from the slab only. This does not include the beam weight. It doesn't mean that we designed the beam without its own weight. It means we have to account for that, and we will see how we do that. And a live load of 2 kips per foot.
So you're encountering 2 different loads, dead loads and live loads at the same time, right?
Absolutely. And this is the case all the time. You will always have that in real life. Why? Because the dead load is coming from the weight of the slab that's dead. It's not moving. It's there, it's just sleeping there. But the live load is the people coming in and out of the building, the furniture going in and out of the building. That's the live load. You will always have those loads, dead load and live load. Is that clear?
Yeah, that makes sense.
Okay, very good. But not all the time you're going to have wind or seismic or snow, or, but you will always have dead load and live load. Very good.
I have a quick question.
Yes.
For grade 60 reinforcement, does that mean the rebar has a yield strength of 60 KSI?
Yes, thank you very much. Yes. It's either we tell you FY 60 KSI or 60,000 PSI or grade 60 reinforcement. The same thing. Thank you for asking that. Now, before we go on, notice the 1 kips per foot and the 2 kips per foot. If you go back to the numbers we punched in the lab for the building the project, you will find these numbers very close. You will find them close to 1 and 2. In these problems, he didn't tell us how we get dead load and live load. But in the lab, we did. In the project, we calculated those from scratch. Compare the numbers and see. You're going to find them close to this. Okay, so those are practical numbers, but he didn't show us how to get it. But in the project, we did that. Okay? So that's all they're given. So before we dive into this, notice that I don't have the cross-section of the beam. I don't know how wide and how deep and all that. I don't know what rebars in there. And I don't know, he didn't give me a moment. Right? He didn't give me a moment. Or he's not asking for how much moment this carries. See, the givens are different. So this is a design problem. That's why we call it a design. All right. So how do we do that? Just follow the steps. First, we need to estimate the beam dimensions and weight. All right. So again, this is one method. You will see in the examples, we're going to handle this similar problem with a different method of design. And we will see which one is the most efficient. I'll tell you. But we need to go through this. So estimate the beam dimensions and weight. Assume H equal 0.1 times L. Remember? He told me the length of the span is 22 feet. So one assumption you can say is 10% of the span. 10% of the span length is the depth. Honestly, a lot of time this gives you too large of a section. But I want to go through it just to go through it. But later on, we're going to use a different method. So you know the length, 22 feet, 0.1 times length gives you the H. Again, this is assumed. 2.2 feet, 27 inches. All right? Now, this is one way to do it. How did we do that in the project? We used the table. Remember, we used L over 18.5. That gave us an H. That H is more accurate or more close to reality than this. See the difference? We're only gonna do this to show you, but usually we will pick the H from the table, and we'll see that. So if H is 27 inches, what is D? Remember we said, let me draw that. We'll do it one time. So this is my beam. I just calculated H as 27. There's H. And then I'm going to have rebar here. And then this is, from here to there is D. What did I say this distance usually? 3 inches or 2.5. Remember that? So if I 27 minus 2.5, it gives me 24.5. See that? So that's an estimate also for D. So that's how this is coming. Now, also assume, look at all these assumptions, guys. Assume B equal half H. And that's what we did in the project. We calculated H from the table, and I told you, assume B equal half H. Remember that? So if H is 27, half of H is 14. 13.5, you round up to 40. All right? Any questions so far? All right. So let's.
Professor?
Yes.
For the height, can you explain again how you taken only 10% times
Yes.
the height?
No problem. So the length of the beam is 22 feet.
I get that. Yeah, I get that one.
Right. Now, one way to estimate the thickness is 0.1 times the length, or 10% of the length. Okay, just one way to estimate that.
So you're just estimating that's 10% of it.
That's it. For no reason.
So it wouldn't be wrong if a student or someone used a different estimation percentage, like 5% or.
No problem. Remember what I said earlier. You can assume anything, but we're gonna check it in a little bit. See that?
Yeah.
Yeah, we're gonna check it to see are we close to that or not. So don't worry, we will check ourselves. But let me get off on a little tangent here. See this 10% as I just mentioned? In real life, from my experience, and when I was a student, not a student, when I first graduated and started working, one of my bosses told me that, and I still remember, and I'll tell you that. This 10% is a magic number, guys. Like let's say, for example, here. Okay, I know the length of the span. Can I estimate the depth of it? Yeah, 10% of that. You're doing an estimate for a project. How much room I should give myself? 10%. You know what I'm saying? You're not sure about something and you want to beef it up. 10%. Believe me, in my professional experience, the 10% works most of the time. Okay, so if you want to estimate something of something What is the ratio between this and that? 10% most of the time works. And then the good news is, like I said, we check ourselves. Okay, so that's just a side note. All right. So we know that H is 10% of the length. D, we said take this minus 2.5 gives you that, and B is half of H. If the depth is this, I'm going to estimate the width as half of that.
Yeah.
Again, it's an assumption.
Get over here.
Can I assume 0.75? Yeah. Can I assume 0.8? Yeah. But when you check, you will see how we're going to verify that. If I have my beam now 27 inches by 14, can I find the weight? Yeah. The weight is nothing but the volume of this beam times 150 pound per cubic feet. Because the volume of the beam is what? The length times the depth times the width. It gives me cubic feet. I multiply by the density 150, it gives me pounds. But I don't want it in pounds. I want the own weight of the beam along the beam. See that? And let me draw that. So if this is my keeps dropping my pen here. So there is the, I don't know why. Ran out of ink, I guess. Let's try one more time. No. All right. Let me do something. I'm gonna move this to the bottom. And I am going to grab the pen here.
Babe, she wants to take my food again.
Okay, there we go. So there's the beam. Okay, and there's the beam. I will take the depth of it and times the length times the width. That's gonna give me cubic feet. I multiply by 150 pound cube, I get pounds. But I don't want pounds. I want pound per foot along the beam, right? That's how W is a uniform load along the beam. So because of that, if I calculate it as length times depth times width in pound, then I have to go back and divide by the length to make sure it's along the beam. So instead of doing that, all I do is what? Multiply by the depth and the width, and then don't multiply by the length, and then you get the answer in pound per foot. All right? And you will see how we do that. All right, so that's it. So what's the beam weight? I multiply by the cross section, 27 inches deep, 14 inches wide, and I divide by 144. Why? Because 27 divided by 12 is in feet. 14 times 12 is in feet. But 12 times 12 is 144. Okay? Then I multiply that by 150 pound per cubic
Babe, I
feet.
can't find my
This
pen.
is gonna be what?
My nice
Feet
pen,
square.
my pen. I don't want to do my work
Look at
without
this.
it.
So feet square is gonna cancel with 2. So my
Yeah, the
answer is gonna
black
be
one.
pound per foot. So
Where?
394. Is that clear? Is that clear?
Where? You hit
Any
it?
question on that? I'll repeat that, and you will see everything is gonna be like this from now on.
Where?
So
far, everything's pretty clear.
okay, good.
So bad.
So another way to do it. So if this is your beam, the cross section, all you have to do is B times H divided by 144 because they're in inches into feet times 150. So you don't have to worry about the length because my answer is going to be pound per foot along the beam. So you don't multiply by the length. Any questions? All right, very
So
good.
why do we want the weight along the beam?
Because remember in statics and structural analysis and deformable bodies, we always have a uniformly loaded beam. We call it W. And the weight of the beam, don't you think it's spread uniformly along the beam? Yes. The own weight of it is spread uniformly along the beam. It's not It's not lumped in the middle. Does that make sense?
Yes, yes. And does the beam weight eventually become part of the dead load, or?
It is, absolutely. It's the
Okay.
majority. The majority of the dead load is the weight of the beam. The majority of the load is the dead load of the beam. Especially if your span is long. Yes, absolutely. Any other questions? Okay. We're running out of time, but let me see if we can finish at least the example. We're not going to be able to finish that. All right. Yeah, we're not going to be able to finish that. It's okay. We can do it next time. Because I want to give you a little break so you can eat dinner or something. Okay. So we will continue next time then. Then in the lab, we will see what we can do along these lines. And I might finish these examples in the lab for everybody. All right. Any question? I want to take attendance, please, before we go. All right. All right. Let's see. All right. Do I have Faisal? Faisal.
Yes, here.
Okay. Abdullah.
Yes, here.
Okay. David. Ismail.
Here.
Okay. Asma. Asma.
Yeah, I'm here, Professor.
Ahmed. Ahmed Isam. No. Okay. Alexis. Sorry. Alexis. Okay. Griffin.
He never calls my name.
Brown. Griffin Brown.
So he knows I'm here.
No. Okay. Janelle.
Here.
Okay. Jacqueline. Jacqueline. I hope I'm pronouncing it right. No. Okay. I think she's the one who's doing the projects and all that. George.
Yes,
George.
here.
Okay.
Yeah, I'm here.
Yes. Garrett.
Here.
Here.
Okay. Joycelyn.
Here, Professor.
Thank you. Arba.
This is the first time he calls me.
Here.
Okay. Andrew.
Here.
Okay. Alexander.
Here. Here.
Benjamin.
Here.
Okay. Binyam.
Here.
Okay. Pablo. Jose.
Present.
Okay. Adis.
Here.
Okay. Andrew. Hong.
I'm here, Professor.
Okay. Gabriel.
Is the last name Iglesia?
No, Mendoza. Yeah. Sorry.
Oh yeah, yeah.
Okay.
Professor.
Thank you. John Paul.
Here.
Okay. Raymond Lamb. Raymond Lamb.
Here.
Okay. Pink Lee.
Here.
Okay. Christian Sean.
Here.
Okay. Jonathan.
Here, Professor.
Thank you. Ravi Michael.
Ravi's here. He just had to get up.
Okay. Montes Christian.
Here.
Okay. Patrick.
Here.
Thank you. Just a few more. Craig.
Here.
Craig Nicholas.
Yeah, here.
Okay. Minwo. Top Park. Okay. Daniel Dang.
Here.
Okay. Prado Berry.
Here.
Thank you. Myra. Myra, sorry.
Here.
Okay, thank you. Hassan. Hassan Saloom. No Hassan. Alexander Shaw.
Here.
Okay. Armando.
Here.
Thank you. Daniel.
I'm here.
Thank you. Ken.
Here, Professor.
Thank you. Paulino. Jed.
Here.
Okay, and then Weston Jean.
Here.
All right, thank you.
Professor,
Yeah, please. Yes.
my name's Ahmed. You called me, but my mic wasn't working.
Okay, Ahmed. Let me see.
Ahmed Assam.
Yes, let me see. Yes, I got you. Okay,
All right, thanks.
you're welcome. All right, so please don't miss classes, and as you can see, we're covering a lot of important stuff, guys. So, and then with that, I'll see some of you in the lab in a few minutes. Okay, have a good evening, guys. Thank you.